Hi, welcome to We Only Rule Out Hypotheses, Not Confirm Them. Let's say we have some new idea in particle physics. Maybe it addresses some deep, long-standing question. And it makes some predictions about things we can measure. Let's say one of the things it predicts is the lifetime of a specific particle. So here on the right, we have plotted the predicted value of this lifetime. It is shown with the predictions error bar. Now we can go and measure the lifetime of that particle. If the measured value for the lifetime disagrees with the model prediction, we can rule this model out. So we do that measurement. And let's say the measured result agrees well with the prediction. Here we plot the measured particle lifetime on the same plot. Its error bar overlaps easily with the model prediction. They agree quite well. This model has passed this experimental test. We can't rule it out based on this result. Now, have we confirmed this model? No. Why is that? Let's look at two reasons. Reason 1. The model could be ruled out by improved experiments in the future. So here again we have the current model prediction and measured value. But in the future we might get a measured result with a much smaller error bar. Note that this new measured value is quite compatible with the old measured value, but it disagrees substantially with the model prediction. So our current model, even though it agrees with current observation, can still be ruled out in the future. As a side note here, we took the initial error bar on the measured value to be much larger than the error on the model prediction, but it could have been the other way around. For example, we could have a situation like this, where the model prediction has a large error bar, but the measured value is known rather precisely. It is possible that in the future the model prediction will improve and its error bar will shrink. This can happen, for example, if the model takes inputs whose values are measured more precisely in the future. So this model can be ruled out if the error bar on the prediction shrinks with time. Here we can see how an improvement in the model prediction can move it out of agreement with the measured value. Either way, even though the current model prediction agrees with the current measurement, the situation can change, and our model can still be experimentally ruled out in the future. Okay, now let's look at the second reason that our model has not been confirmed, which is that our model is not the only one which can agree with the current predicted value. Again, here we have our model prediction in good agreement with the current measured value. But we could write down some other model which also agrees with observation. As long as more than one model can agree with the current observation, we can't claim any of them are confirmed. So for those two reasons, we never confirm hypotheses. We only rule them out. Even if we have a model that is in agreement with all known experimental results, we cannot confirm that that model is the true model of nature. It just means that it agrees with all of the tests so far. So then, if we have multiple models that all agree with observations, does it matter which or if one is right? If we have at least one, isn't that good enough? Not in the long run. The models may be experimentally indistinguishable now, but they may not remain that way. Let's see a couple ways this can happen. So in the first way, the models may make very similar predictions, both compatible with the current measurement, but the experiments eventually get precise enough to detect the difference between the two predictions. So here we have two models which are both in agreement with observation, but measurements can improve, allowing us to rule out one or both of them. In the case shown at right, we would rule out Model 2, but keep Model 1 for future testing. The second way is a bit more subtle. Here, let's say we have two models whose predictions are so close that no experiment can tell them apart. A hypothetical measurement, whether it has a large error bar or a small one, cannot distinguish between these two models, as any experimental result that is in good agreement with one of the models will be in good agreement with the other as well. The error bars on the predictions of the two models could shrink and make them experimentally distinguishable, but for argument's sake, let's say that isn't going to happen anytime soon. In this case, it might seem like the difference between Model 1 and Model 2 is merely academic. We can never tell if one agrees with measurement and the other doesn't. But future technological advances may allow us to measure other quantities or measure these same quantities under a wider range of conditions. This means that in the future, there may be some quantity for which the models may have very different predictions, even if there isn't one now. If that happens, then an experiment can rule out one or both of them. This brings up a point about how science progresses. With time, experiments are conducted under an increasingly wide range of conditions. Depending on the experiment, this might mean varying parameters like temperature or where the experiment is conducted. In particle physics, it often means conducting experiments at different energies. And one can even consider cases like experiments done in zero gravity on the International Space Station. Now, it may be that within a certain range of experimental conditions, two models' predictions are almost identical. But under other experimental conditions, the models may make very different predictions. So with time, as experiments are conducted under a wider set of conditions, the two models that initially appear experimentally indistinguishable may become distinguishable. While they appear to predict essentially the same things initially, eventually one may fall out of agreement with experiment while the other continues to agree. A classic example of this is the case of Newtonian mechanics versus special relativity. In experiments where all of the relevant speeds are far below the speed of light, the two models predict almost identical behaviors. Detecting the difference requires very precise measurement. On the other hand, at speeds approaching the speed of light, their predictions deviate from each other significantly. Early measurements were all made at low speeds, so no hints of special relativity could be detected. But today's experiments are easily able to distinguish special relativity from Newtonian mechanics and show that Newtonian mechanics does not match reality. So models that today look experimentally indistinguishable may be able to be distinguished in the future as error bars get smaller or experiments measure more things or measure the same quantities under a larger set of experimental conditions. And eventually, one or both models may be ruled out. Okay, let's summarize what we've seen. Even when a hypothesis agrees completely with observation, we cannot confirm it. This is because 1, we cannot know that future experiments won't rule it out, and 2, we do not know that other hypotheses don't agree with observation similarly well. And if we have several models that agree with all known observations, we can't tell if one of them is a better description of nature than the others. But that can change in the future as experiments improve. Our understanding of the laws of the universe always differs from the actual laws of the universe. We see some phenomenon and we make a model of it. In fact, we may make a few models. But because we keep models that agree with experimental results, and those experiments become more precise and are done over a wider set of conditions over time, our models improve. And thus the difference between the laws of the universe and our understanding tends to get smaller with time.